All right, I have drawn certain things because it might be difficult for me to draw on the fly. So we have considered the ground state, one particle in the ground state, another particle in the first excited state. And we were talking about the probability distribution of finding the two particles. So for the first particle, since it is in the ground state, the mod psi square will be a curve like this. It will have a higher probability of being found at the middle, lower probability of being found at the edges, and things like that. And the first excited state, the function it was actually a function like this. And if you take mod psi square, it becomes a function like that. So it has zero probability of being found at the middle and higher probability at the two sides and things like that. Now we are considering a situation where there are two particles. When we consider two together, they will have a high probability of found in these 2 points. Okay, because x1 is having a central value here, which is large. So x1 has the highest probability of being found here. X2 has the highest probability found at two different places. So these are the 2 points that have the highest probability. And if you draw the probability distribution, these are like sort of, you are looking at a mountain, but in case of the two-dimensional thing, they will actually be two mountains. And the tops of the two mountains are the places. Two mountains are the probability of finding the particle in different parts. That will be like a surface, and that surface will have two peaks oriented this way. Clear? And now if we draw the equiprobability lines, then all these points will have the same probability. That means the probability of finding x1, well, here you have to look at this, right? X1 is this value. X1 at this point and x2 at that point is having a particular value of probability, and all these points share the same probability. So we have an equiprobability line. Similarly, this is an equiprobability line. This is an equiprobability line. And similarly, there will be such equiprobability line in the other peak also. That there are two mountains oriented this way, and these are the equal probability lines. What I drew in the last class was, if you look at it from the top, like a plan view, then you see those contour plots. So it will look like a circle here, another circle there, another circle there, oriented in a particular direction. Now, if we consider the first particle in the first excited state and the second particle in the ground state, then the orientation changes. It still has two peaks, but the orientation changes. The first particle will have two peaks. The second particle will have one peak. So the combined surface will have two mountains. And again, you can draw these equiprobability lines. And again, if you look at it from the top, you will find the other picture that I drew in the last class. Is that clear now? Do you have any question? If there is some question, then I can go into it, or then I will proceed forward. I'll wait for another 5 seconds, and then I'll go ahead. If there's no question, let's go ahead. Okay, let me erase this place.
So,
yeah.
Question, not in this, in Pauli matrices.
Yeah.
Sir, so we got the Pauli matrices in the spin space also, and we also know that the Pauli matrices span the Hilbert space. So, is there any connection between?
No.
Hilbert?
Pauli matrices do not span the Hilbert space. Well, Pauli matrices are representing operators. So see, if you consider what we did in the last semester or the early part of this semester, the Hilbert space actually all the state vectors live in the Hilbert space, which means that the wave functions live in the Hilbert space, not the operators. Okay, all wave functions live in the Hilbert space, including the basis vectors. They live in the Hilbert space. In case of spin, it is not the Hilbert space I was talking about. I said let there be a separate space considered for the purpose called the spin space, because these are 2 by 1 matrices, right? But then the Pauli matrices actually represent operators. Operators for observing, operators are always related to observation. Observation of the spin in the z direction, observation of spin in the x direction, observation of spin in the y direction. The Pauli matrices represent that. Therefore, Pauli matrices are not members of the spin space. Yeah.
Okay, sir. Thank you.
Excuse me, sir.
Yeah. I've just deleted
So
and you
we
asked.
can
Yeah.
represent the spin in X as a linear combination of spin in Z. What does it mean?
Okay. Spin in the z direction. That means if the magnetic field of a Stern-Gerlach apparatus is oriented in the z direction, then we would like to describe the spin state in some kind of a basis, and it will be convenient to express in the z basis. Z basis means up z and down z. That becomes the basis. Basis is something that it is complete in the sense that any vector can be expressed as a linear combination of those basis vectors. So if I have another vector, another spin state oriented in any n direction, that can be represented as a linear combination of the two z basis vectors, up z and down z. And
Does it mean
yeah, if it can be done for any n vector, it can also be done for any x vector. That means a vector that's oriented in the x direction. So up x, for example, that's also a vector. That vector can also be represented as a linear combination of the bases, and the bases are my up z and down z.
yeah?
Any question? Is there anything that I need to clarify after this? See, my problem is that when I'm in a class, regular class, I can look at your eyes and I know who is understanding, who is not. If there's a puzzled appearance in your eyes, I know that I have to repeat. But I don't see your face, right? So you have to speak up. You have to tell that this is something that you didn't understand. Sir. Can I continue?
Yes, sir.
Okay. Now we come to a very profound aspect of quantum mechanics. Something again that does not have any similarity in classical day-to-day objects. The fact that quantum particles are identical particles, non-distinguishable particles. It means that there is no difference between two electrons, there is no difference between two alpha particles, there is no difference between two, say, protons. So they are identical. And what kind of effect does that have? Let me illustrate that by giving an example. Suppose two balls are colliding with each other. One ball is here, another ball is here. And they're coming to each other and colliding with each other. And suppose they are so they will come, and this one will come, and they will collide, and then one will go in this direction, and the other will go in this direction. And if you have some kind of a detector here, then you can detect and you can tell that this is particle number 1 and this particle number 2, and you can tell that the particle number 1 came like this and arrived here, and particle number 2 went like that and arrived here. Or there's another possibility: particle 1 starts from here, particle 2 starts from here, and they go towards each other, and here is a detector, here is another detector, and then this one gets deflected that way and goes here, and then deflected that way after the collision. So now you know that particle 1 and particle 2, which one went to which detector. So when a detector clicks, you know something has been received, and then you can always look and find which ball has been received. Right? So this is the behavior of a classical particle, and this is possible because you can trace their trajectories, and you can find out which one went where. But if you consider again now an electron, suppose the electron is being released from here, and another electron being released from there, you will not be able to draw a trajectory like this. Okay, so you will need to draw something like a fuzzy picture, something like this. Okay, something like fuzzy picture, and then you don't know what happens here. And then after that, you know that something went this side, something went that side. And if you have detectors, then they get detected. You might say that, well, when a particle is in this side and another particle is in this side, then you can distinguish them by means of their position, because they are at different positions. But when they come here, there will be no way to distinguish between one electron and another. And when they arrive here, you can only say one electron arrive here, another electron arrive here, but you will not be able to say which one is arriving here, which one is arriving. And this character, that they are indistinguishable, has profound impact in the behavior of things around us. This is very counterintuitive, but it's actually what happens. So the actual particles in reality are quantum particles, and the quantum particles have this property that they are non-distinguishable. Even in this kind of experiments, we see the signature of these being quantum particles, non-distinguishable particles. Now, from a quantum point of view, if you see that something has arrived here, then there are two possible ways by which a particle could be arriving here. One is a particle like this going here, the other is the particle like this going here. And they're ultimately, when they are received, non-distinguishable, so you don't know which one is received. So there are two possibilities, and whenever there are two possibilities in a quantum system, there is always a possibility of interference. So if instead of a detector that detects only this, if you arrange such a way, if you arrange in such a way that there is a array of detectors, in this point there's a detector, in this point there's a detector, and so on and so forth, all these points has a detector, so you know where things are being detected, then you'll be able to see the effect of the interference. And actually what we'll see is that the particles will be distributed in somewhat like this. It is supposed to be. Most of them are supposed to be arriving here, less arriving there, so it is supposed to be something like this, right? Expected. But what we actually see is that there is slight deviation from there. Which means that along with this, there is a interference pattern. There is an interference pattern associated. Something like that. And this happens because the particles are non-distinguishable. So indistinguishability can give rise to a completely new phenomenon that's not expected if they are distinguishable particles. Now, our task now is to devise some way of representing this non-distinguishability of particles. And how do you do that? In the last class, we have seen that if there are two particles, then the combined eigenfunctions, psi 1, 2, we said, can be represented as the individual eigenfunctions. Suppose this particle is in nth eigenstate, and that particle is in the kth eigenstate, and then we had put the first, suppose first one is in up state, sorry, is in the up state, and the second was in the down state in the z direction. Then we saw that we can represent a combined state of two particles in this form. Now, what this indistinguishability demands is that if we swap these two positions, if we swap 1 and 2, it will give the same result. So, if we swap, then you get this. Psi n will be the state of x2, and psi k will be state of x1, and this one will be up 2, down 1. This is definitely not the same as this. So whatever we did in the last class, this does not suffice in representing identical particles. Now, it so happens that nature allows only two possibilities. These two being identical means their effective result should be identical. That means mod psi square of this one, mod psi square of this one should be the same thing. Now, nature allows only two possibilities. One possibility is, let me write. Because I know what I'm writing, you're also writing. So, whatever I need you to remember, nature allows only two possibilities. One is psi 1, 2 is equal to psi 2. The other is psi 1, 2 is equal to minus psi 2. In both cases, the result is the same, because ultimately what matters is mod psi square, and therefore the both of these give the same results. But this is called a symmetric wave function, and this is called the antisymmetric. So these are the only two possibilities. And the particles that obey this character are called the bosons, and the particles that obey this character are called the fermions. And the whole universe, there is nothing other than bosons and fermions. So all particles are divided into two basic categories, bosons and fermions. Those which give rise to symmetric wave functions are bosons. To give us the anti-symmetric wave functions, they're fermions. I'll have to illustrate that much in detail. So I will go step by step. This contains two parts, the spatial part and the spin part. So let us separate them out and let us consider each one separately first. First, the spatial part. Okay. So first we consider spatial wave function. And that is the eigenfunctions are psi, x1 function of x1, x2, psi x1, x2, and we have seen that that can be written as, that means I'm talking about the eigenfunction. This is not just any wave function, this is eigenfunction. And we have already seen that eigenfunction can be written as the product of the individual energy eigenfunction of the two particles. So these are psi n x1 and psi k x2. This is something that we've seen in the last class. And your psi x2 x1 uta is equal to, now in this case, psi n x2 and psi k x1. So I am basically the logic that runs through this whole identical particle business is that if I swap the 1 and 2, that will make no difference. So that is the basic idea. So what we then demand is that out of this, what we then demand is that psi x1 comma x2 mod square is equal to psi x2 x1 mod square should be equal, because ultimately what matters is the mod square, because that is what gives the probability of finding the particle at different places. So these should be identical. Now again, in this case, there are two possibilities. Psi x1 comma x2 is equal to psi x2 comma x1. This possibility 1, and the other possibility psi x1 comma x2 is equal to psi x2 comma x1 minus. And obviously this is a symmetric eigenfunction, and this is an anti-symmetric. Okay. So these are the two possibilities in order to satisfy this. You might argue that what if we multiply a e to the power I alpha t kind of phase factor? Then also this is true, but yes, that doesn't happen. So the fact that these two are independent of our times, and therefore these are the only two possibilities that have been found in nature. So this is just a fact. Now the question is that these two, after all, if you swap, they are not the same. So this is the demand, but actually these are the psi n, psi k, and this, that, and these two are not the same. These two are not antisymmetric either. So this is neither symmetric nor antisymmetric. How do we handle this? How do I get something that satisfies either of these conditions? Now, in order to do that, I need to put some space. In order to do that, we note that the Hamiltonian operator, when operated on this, we have done in the last class, then that gives the eigenvalue E, which is nothing but the sum of the two individual eigenvalues. Suppose this one has the eigenvalue En, this one has the eigenvalue Ek. So En plus Ek is the total, and then this is the eigenfunction of the Hamiltonian operator with eigenvalue E. So basically we have seen that psi x1 comma x2 is equal to E psi x1 comma x2. Last class we have seen that. And this is also true for the opposite one. That means the Hamiltonian operator operating on psi x2 x1 is the same E psi x2 comma x1. Now, whenever we have this kind of a situation, then then it is possible to define a new function out of these two eigenfunctions. Suppose there are two arbitrary any two functions, psi A and psi B. So suppose there are two functions, psi A and psi B. Just prove that. So all that we demand is that when a operator operates on psi A and psi B, both give the same eigenvalue. Both are the eigenfunctions of the operator and both give the same eigenvalue. There are two different functions. So if that is true, then we can write the Hamiltonian operating on A psi A plus B psi, sorry, this will be small psi, because these are the eigenfunctions, the time independent eigenfunctions. So if you write this way, then you can write A Hamiltonian operating on psi A plus B Hamiltonian operating on psi B is equal to, this will get E out, this will get E out, so E comes to the front, again it becomes A psi A plus B. So you see that this becomes then the whole thing becomes also another eigenfunction of the Hamiltonian operator with eigenvalue the same, which means that we have a situation where these individual components, each individual two things, which we found to be, if we reverse the positions of 1 and 2, they are not symmetric, not antisymmetric either, but we might try to construct a new eigenfunction as a linear combination of these two eigenfunctions, the way we have done it here. If these two are the eigenfunctions, a linear combination is also an eigenfunction with the same eigenvalue. So we can, this will work only if the operator for both, when operator on both give the same eigenvalue, then it works. And in this case, it is true. And therefore, we can then try to construct psi plus x1 comma x2 as this one, psi n x1 psi k x2 plus psi n x2 psi k. Let me erase this part, otherwise I will proceed. And another possibility is psi minus, simply I have added these two, right? X1, x2 is equal to psi n x1 psi k x2 minus psi n x2 psi k. You can easily see that these are not normalized, and therefore, in order to normalize it, I have to multiply that by 1 by root. So without normalization, nothing works. So we have defined specific, what should I say, linear combination of these two. In place of A and B, we have not put anything, just 1, 1. But let's see if these satisfy the requirements of being symmetric and antisymmetric.
Sir,
Yeah.
sir, I have a doubt in that
Sure.
line where you have written that psi A and psi B are different eigenfunctions of A.
Yeah.
I don't understand that because psi A into psi B should be like the multiplication should be the eigenfunction, right? Because
No.
psi of x.
No. I have in this line, I have assumed that psi A and psi B both are eigenfunctions of the Hamiltonian operator with eigenvalue E. Okay,
Okay, sir. Okay.
so it is sort of a situation where there is a repeated eigenvalue with different eigenfunctions. You have come across that in linear algebra. It happens most of the time. So there are situations where there are repeated eigenvalues for different eigenfunctions. You can always define different eigenfunctions with the same eigenvalue. And this is a situation like that. If that is true, then you can do this and you can define a new, uh, well, it is something like, you have seen that there is a situation where there is a plane and there is another vector. Along this, it may be unique, but in this plane, there is a same eigenvalue. You have seen that, right? In this kind of situation. And any two eigenvectors in this direction can be taken as the basis vectors, and on that basis, any other uh, eigenvector can be defined. All that you have done, right? Here we are doing something similar. The psi A and psi B are these two, and we are only defining a new vector which is a linear combination of these two vectors. That's also in the same plane, and therefore that's also an eigenfunction.
Okay, sir. Actually, I thought that psi A was psi k of x1, so that's why I got the confusion.
Yeah, no. Here I'm doing a general thing, and later what I'll do is that in place of psi A, I will put uh, only this part, and psi B I'll put only this part. Since both are eigenfunctions, I can do that. Here. Okay. Now this is we now need to check whether we have achieved what we wanted to achieve. We wanted to find something, some kind of eigenfunction that is either symmetric or antisymmetric, which will then be able to represent identical particles. Now, let us do it for the negative one, and I'll leave it to you to do the positive one. Okay. So for the negative, because I've written it, it's a second, I can continue with that. So I'll need to then write minus x2 comma x1 by swapping the positions is equal to 1 by root 2. It will be psi n x2 psi k x1. I'm swapping the positions minus psi n x1 psi k x2, right? And then you can see that this is nothing but the negative of this, because psi k x2 psi n x1 is here, psi n x2 psi k x1 is here. So I can see that this leads to psi minus x2 comma x1 is minus psi minus x1 comma x1. So this is antisymmetric. This satisfies the condition of being antisymmetric. So I can see that this function, whatever we have defined, is then antisymmetric. And in the similar way, you will be able to check just by reversing this. You'll find exactly the same thing. So this is the same as psi plus x2 comma x1. So symmetric. So simply by adding and subtracting the two things that were earlier found to be neither symmetric nor antisymmetric, we have been able to construct symmetric and antisymmetric eigenfunctions. Okay, these are the two things. Okay, let me delete this line because this we have already done. Some space. So this is symmetric and this is antisymmetric. So we have been able to define things that are symmetric and antisymmetric. One interesting thing you might note at this stage, that suppose for the spatial case, n is equal to k, what happens to this? For the spatial case, psi minus x1, x2 becomes 1 by root 2 psi n x1 psi n, because k is equal to n, x2 minus psi n x2 psi n x1 cancel out equal to 0. Now this, if I express in words, can be said like this: it is impossible to construct an antisymmetric eigenfunction for particles in the same state. Okay, so where the particles, two particles are the same state, n is equal to k means both are in the same state, in spatial state. Both are in the same spatial state. Then it is impossible to construct a antisymmetric eigenfunction, but it's possible to construct a symmetric eigenfunction. There's no problem with it. Okay. And later I will come back to this, and you will see that this has profound implication in physical reality, because this is at the base of the Pauli exclusion principle. The particles that obey this equation cannot have the same state. No? This is at the base. So that's interesting. But I'll come back to that, because that requires a little more discussion. After having done spin, I'll do that. So at this stage, up to this stage, is there any question? Then I'll go to spin. I have to consider, I said that first I have to consider the spatial part and then the spin part. I have considered the spatial part and constructed symmetric and antisymmetric eigenfunctions. Now I'll have to do that same thing for the spin. Is there any question up to this? Just keep these two functions very clearly written, boxed way in your copy, because this is something that we have to come back to. Because the two things we have been able to construct, these spatial eigenfunctions that will actually work for identical particles. Let me read that. Now let us go to spin. Spin, there are two particles, and we are only considering spin in the opposite direction, or the z direction. So there are two possibilities. First particle can be up, second particle could be up, first particle could be down, second particle could be down, so on and so forth. There are four possibilities. So the four possibilities, let me write four possibilities. The first is, in our convention, up, which means the first particle is up, second particle is also up. Second possibility is down, down, which means first particle is down, the second particle is also down in the z direction. Third possibility is up, down. The first particle is up, the second particle is down, and the fourth possibility is down, up, which is the first particle is down, the second particle is up. I'm asking you to, I'm writing this explicitly because I want to get into your head that this convention is a positional convention. This means that the first particle is up, second particle is down. This is not the same as this. Okay. But then we will demand that if I now exchange the positions of 1 and 2, it should lead to the same thing. It should lead to the same thing. Now that is required of something that can be called a representation of identical particles. So we exchange levels. So we exchange levels. I see that if I exchange the levels, this one becomes 2, this one becomes 1, this remains the same. So the first one satisfies the condition of being symmetric. Second one, I exchange the levels 2 here, 1 here, it still remains down, down, and therefore that also is a satisfies the demand of being symmetric. But this one, if I reverse the position, is not the same as this, and therefore that does not. So we find that the first one, let me write up, up, and down, down are symmetric. And therefore, these conditions do represent the character of identical particles. But then we will do the same thing the way we handle the situation in case of the spatial wave functions. I see that these two are neither symmetric nor antisymmetric, but let us check out if we add them and subtract them, we do get something that is meaningful. So let us first add them. This is up, down, plus down, up. Is that this is really the first up? I need to write it explicitly so that you don't mistake. This is down 1 and up 2. So this is actually this. And now swap. If you swap their positions, it becomes, it is, the first one becomes down, this one becomes 2, this one becomes 1, and so on. So we swap the positions of 1 and 2. If you swap it, then you get, this becomes, okay, let us write and then up, 2, down 1, plus down 2, up 1. Now in our positional convention, this will be a down first, because the first one is in down state, the second one is in up state, plus this one is, first one is in up state. Okay, sorry, first one and the second was in down state. So you started from this up, down, plus down, up. We ended up in this, which is basically the same, right? This is only written later, but basically the same. So I see that by adding this, I get something that is symmetric. So this also fits our bill of representing identical particles. Now let us try out the negative one. Let's try out the negative one. The negative one is up, down, minus down, up, is equal to up 1, down 2, minus down 1, up 2. Now swap. You get, I'll not write equal to, up 2, down 1, minus down 2, up 1. Now you so notice that this is nothing but this but with a negative sign, because now this one had a positive sign up down. This is, let me write it correctly. One was down, this one was up, minus one was up, two was down. So you notice that this is actually negative of this. Okay, so this is then antisymmetric. So we have been able to construct both the spatial part as well as the spin part by doing some very simple linear combination, plus and minus. We have not multiplied with any coefficient, just plus and minus, that yields symmetric and antisymmetric, both a eigenfunction as well as a spin state. So then we will be able to write that we will notice that, let me just summarize because only 5 minutes left. Let me summarize. Then up, up, comma, down, down, and up, down, minus, plus, down, up. These are symmetric. And the other one, up, down, minus, down, up, is antisymmetric. These results are actually important. You later find that we'll need to use these results again and again. So it is good to have this boxed off in your class note. So there are 3 symmetric states and 1 antisymmetric state. Okay. In the next class, we will see if we then have this kind of state, 2 particle state, this kind of 2 particle states, and then we operate that by some kind of a spin operator. What is the eigenvalue? Whether they satisfy the condition of being eigenfunction, eigenvectors or not. These are the things that we need to check. But at least we are satisfied that we started with these 2 possibilities, or these 4 possibilities. We found that these 2 actually fit the bill, but these 2 do not. But by making linear combination of these 2, we have been able to construct symmetric and antisymmetric spin states, 2 particle spin states. And we'll then need to check later whether they are really eigenfunctions of the usual spin operators like Sz, S square. Of these operators, are these eigenfunctions? If so, what are the eigenvalues and things like that? That we have to check. But at least we have been able to construct things that fit the requirement of representing identical particles. So I'll end today. If there is a question, there is a minute or 2 we can answer.
Excuse me, sir.
Sure.
Sir, when we began the lecture, when you were describing the 2 particle thing, like their collision, and we placed detectors to detect them. So when we place the quantum particles, you said we get an interference pattern. Can you tell a bit more about it? I didn't get it. How do we get the interference pattern when we observe those?
Because the 2 particles are identical. When they collide, that means they come. Their better expression would be that initially their wave functions, wave packets, are physically separated. Can you see me in the image? Yeah, they're physically separated, but when they come close, at some point in time, their wave functions, the wave packets, sort of overlap. The moment they overlap, it is impossible to find out which particle is where. You can only say that there are 2 particles in this region, right? And after that, you find that one particle goes this way, and another particle goes that way, and it's impossible to tell which particle went that way, which particle went that way, right? This is what has happened in a quantum picture. Therefore, in a quantum picture, if there are 2 ways by which a particle can be detected at a detector, There are two ways. Either it can come like this, or it can come like that. When there are two ways, the two possibilities will interfere. There will be interference pattern. And that is the interference pattern that's actually observed. Whenever you have a scattering between electrons, we do see an interference pattern. And that's because of this. Because the electrons are indistinguishable particles.
Sir,
Okay. Yeah.
yeah. So one thing we predicted, like you draw a sine kind of like curve.
Center. What?
You
Oh yeah,
no.
yeah. No. What I said was that there are normally, if there are distinguishable particles, you would expect most of them to be detected here, less here, less here, less here, and all that. But what actually happens is that you get some kind of a curve like this. Huh. So which means that this curve, along with a some kind of an interference pattern, sinusoidal like thing. Interference patterns are always something like this, right? So what happens is that this, along with this, is what is actually observed. Yeah.
Got it, sir. Yes, sir.
Excuse me, sir.
Yeah.
Sir, what happened to the electron? They follow the dual nature. Okay, what happened to the particle part of the electron when the wave are interacting? I mean, when they are come close.
Oh. Answering this question will take a little more time. The time is up. So the next class I'll start with this question. Okay, just remind me that this question was there. And this question
Okay.
is not only related to the example that I showed, it's also related to, for example, the double slit experiment. Uh, when we have the wave character, what happened to the particle character? Then also the same question appears. So that has to be answered in a more general sense. That's why I'll take a
Okay,
little more
sir.
time to answer that question.
Okay.
Okay, let's finish.